So we have seen how we can represent rational numbers and irrational numbers on the number line, right? Okay. Now let me give you one more example. For example, if someone says ki find out an irrational number between these two decimals, let's say 0.2 and let's say 0.5, let's say. Okay, let's make it 0.2. This is 0.2. This is point 0.2 is a rational number. 0.5 is a rational number. As I told, there are infinitely many rational numbers also in between these two, and many irrational numbers also in between these two numbers. Okay, so someone says ki, okay, just tell me one irrational number between these two numbers. Okay, rational numbers I can easily tell. Rational number, for example, 0.3, 0.4, 0.31, 0.32. Likewise, we can tell many 0.425. These are all rational numbers in between these two numbers. But how to get an irrational number? So for rational numbers, the decimals that are rational, either they will be terminating. I have told this, we have discussed already, but still we are revising. So either it will be terminating like 0.3, terminating decimal. Okay, nothing after 3. Okay, these are all terminating decimals. Or it can be non-terminating but recurring. Those decimals are also rational. What I mean by recurring, let's say 0.6666. So this number 6 is recurring, or 0.23232323. These are all recurring. The same number 232323 is repeated. Okay, so these are all non-terminating but recurring, so they are rational numbers. Okay, rational numbers we denote by q. Okay, we denote by q, rational numbers. Okay, so terminating decimal or non-terminating but repeating decimals are rational. Irrational decimals are, how are they like? For example, 0.61498 random numbers after decimal, non-stopping. It cannot end. Okay, unlimited number of numbers, that means so many numbers, and there is no pattern. Like here we had a pattern 2323, recurring, repeating, the same numbers are repeated. Nothing is being repeated here, and it is never ending also. Such decimals are irrational. Okay, so here only, if I want to give an example of an irrational number between 0.2 and 0.5, I can say 0.2, and then to represent, because exactly we cannot write the whole decimal, it is never ending, so we cannot write the number exactly, but we can give a feel of it. Like for example, if I say 0.201 for example, like this, unlimited. So this is what I have represented, or non-terminating, that is not ending. Okay, this goes until infinity, and there is no pattern. The same set of numbers are not repeated, right? Initially it is 0 1, then 0 0 1. So it's not, we this pattern doesn't meet the criteria. The same number should be repeated. Like example, 2 3 2 3, the same number 6, the same set of number is being repeated. Here nothing like that. Okay, so this is an example we can give like this if we want to give it in the decimal form. Okay, fine. So this is an irrational number between zero point 0.2 and 0.5. Okay, non-terminating, not recurring decimal. So like this I can represent an irrational number. Okay, so irrational numbers, otherwise all the root 3, root 2, so these numbers, or 3 to the power 1 by 3, 4 to the power 1 upon 5. So these numbers, okay, we'll learn the rule of exponents, but these numbers, okay, pi, the number e. So these are all irrational numbers. Okay, these are irrational numbers. If you try to convert them in decimal, if root 3 will try to convert in decimal, it will be 1.732 something 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 random numbers until infinity. Okay, so this is an irrational number. Fine. Now we'll see what do we mean by the rationalization of the denominator. Okay, so okay, so before learning the rationalization of denominators, this identity we must be knowing that. Okay, what is this? Let's find out. A plus b, a and b are any numbers, and a minus b. So this is what, if we multiply a into a square, then a into minus b is minus ab, then a into b is plus ab, and then b into minus b is minus b square, right? So this cancels out. This is a square minus b square. So a square minus b square can be factorized, can be written in the form of product of its factors, is like this. Okay, so 6 square minus 3 square is what? 6 plus 3 times 6 minus 3. So this is the basic identity that we'll find the use of. Okay, so what do we mean by rationalization? Okay, that means the denominator of the fraction representation we are going to make rational. For example, 1 upon 3 plus root 2. The numerator is a rational number, but the denominator is an irrational number. Okay, so we'll try to use the same identity, multiply by 3 minus root 2 here also. So essentially this is 1, right? So the numerator is what? The numerator is 3 minus root 2 only, and then the denominator is what? A plus b times a minus b is a square minus b square. We just saw this, right? A plus b into a minus b is a square minus b square. Same property or the identity we'll use here. Okay, this is going to be 3 square minus root 2 square. Okay, that is 3 minus root 2 upon 9 minus 2, that is 7. So 3 minus root 2 upon 7 is the rationalized form. That means the denominator is now a rational number. Okay, so this is what I mean by rationalizing the denominator. Okay, another form can be like this: 1 by square root of some number x plus square root of some number y. How to rationalize this? Again, very simple. Multiply by this number, this is y, so this is 1. We are multiplying by 1, so we are not changing anything. This thing I have to make the denominator rational. Do like this. This is what? Root x minus root y upon root x whole square, that is x, minus root y whole square is y. So this is the rationalized form where the denominator is now a rational number. For example, so this thing was of the form what? This example was of this form: 1 upon x plus root y form. This form, okay, where x is 3 and y is 2. Okay, this is root y, root 2, correct? It can be in this form also. So like this. For example, if I take, what is the, now rationalize the denominator for this, let's say 5 upon root 7 plus root 2. How to rationalize denominator? Rationalize the denominator, simple: root 7 minus root 2 and root 7 minus root 2, multiply like this. Numerator becomes this upon, this is 7 minus 2, that is 5 only. So this is what? This is 5, right? So 5 cancels out. This is root 7 minus root 2. Okay, so this thing is the same as this, root 7 minus root 2. Now the denominator is 1 for the thing. Here the denominator was an irrational number. We have rationalized the denominator. That is what we have done. Okay. So this is a very useful technique in many questions. We'll be finding use not only in this chapter but for chapters to come also. Okay. So we have seen the real number line has rational numbers on it and irrational numbers on it, right? And we have seen the definition of rational numbers. Fine. So we have seen that this real number line has rational and irrational numbers. Rational numbers can be represented in the P upon Q form, okay, where P and Q are integers, where and Q is not 0. This is what we know about the rational numbers. Okay. Now, if someone says, and there are infinitely many numbers between any two number on the real number line, just pick any two numbers on the real number line. There are infinitely many rational numbers also and infinitely many irrational numbers also between the two selected numbers. Okay, just select any two numbers, whether rational or irrational, just any two numbers, no matter how close they are also. So there are infinitely many rational and irrational numbers between the two selected numbers. Fine. So if someone says, okay, let's say find out, let's say as we just said, that there are so many numbers between two. So someone says, okay, find me, let's say there is a, this is a rational number 2 by 3, and let's say 5 upon 7, anything. So find out, let's say three rational numbers between these two. Okay, find out three rational numbers between these two rational numbers. So what should I do? So there can be many ways to find this out. So one thing is the mean is what? uh, so one method can be, see, the one method can be here, first method, that you just balance the, make the denominator same. Okay, so this one I multiply by, let's say, 7. Okay, that is essentially multiplying by 1, so this becomes 14 by 21, and this one if you multiply by 3 and 3, this becomes 15 by 21, right? Now the denominators are the same. Now you have to just find three numbers between 14 and 15, that we can do, right? So between 14 and 15, let's write three numbers: 14.1, 14.2, 14.3. Okay, and then divide by the same denominator, 21, 21, 21. These are three rational numbers. These are all rational numbers. Okay, I have represented. So in other form I can write this as 141 upon 210, right? 142 upon 210. So like this I can write all these numbers are in P by Q form, hence they are certainly rational numbers. Fine. So this is how we can write. Make the denominator the same, and then you can write like that. Another method can be by finding the mean. Okay. So another method can be by finding the mean. Let's say you have to find A and B. Two numbers are given. Two numbers are given, let's say. So the mean, that means mean means what? The average. A plus B upon 2 will be a number in between, right? This is midpoint actually between the two numbers. The numbers at, no, midpoint, equidistant from A and B, in between. So A plus B upon 2 is a number in between the two, greater than A and less than B. Okay, if I say that A is lesser than B. Okay. So this number here is A plus B by 2. So can we find out this number between a and a plus b by 2? Yes, this number here will be what? This will be a plus b by 2, this number, then average of that, okay? This number and this number, the midpoint is this number. So this will be what? This will be 2a 3a plus b by 4. This is this number, 3a plus b upon 4. Similarly, I can write this number also, right? In between a plus b by 2 and b. Okay, this is going to be what? Yes, this is going to be likewise a plus 3b upon 4, right? A plus 3b upon 4, this number. So these three numbers, 1, 2, 3. Given a and b, I wrote the three numbers in between the two given numbers. Okay, fine. And a and b can be rational, irrational, both. Okay, it's not necessary that they be rational only, but in the first method, since the form you made it in was p by q form, so this is possible for only rational numbers, the first method. This method, any number, it's true, whether rational or irrational, this will work. Okay, for example, if I give you, maybe you cannot represent it in p by q form or decimal form, but for example, let's say your a was, let's say for example your a was, let's say root 2, and this was root 3, square root 2 and square root 3. So what is this number? This number will become root 2 plus 3 times root 3 upon 4. This number is root 2 plus root 3 by 2, isn't it? This number becomes 3 times root 2 plus root 3 by 4. Sorry, this is 4. Yeah, 4. 4. So the three numbers, they are irrational, of course, but they are numbers in between. So if I write them in this form, certainly this is a number. Maybe we cannot represent that, the number in between, in the p by q form. Of course we cannot, because it is not rational. We cannot represent it in decimal or p by q form like that. Okay. Another method of finding numbers between two given rational numbers, if I say rational numbers. So let's say there is a rational number a upon b, and let's say another is c upon d, and let's say this is c by d is more than a by b, let's say. So if a, b, c, d, all the four are positive, okay. So if a, b, c, d, they are positive, of course, if they are negative also, we can find out at least the magnitude, that which number is more than magnitude, and then we can manipulate accordingly for the sign. Okay, so if a, b, c, d are positive numbers, so I can simply, what I can say, a by b, so just add the numerators and then add the denominators. This is going to be certainly in between the two, certainly. Okay, means what I mean to say by this, if I give an example, let's say find out 2 by 3 is a number, another one is, let's say, any number, 6 by 7. Okay, so which one is more? This is more. Okay, 6 by 7 is more. Okay, so how do we find out which number is more? 7 into 2 is 14, 7 into 2 is 14, and 6 into 3 is 18. Okay, so this one is more, right? So this is also going to be more. Okay, that said, so 2 by 3 and 6 by 7, 2 by 3 and 6 by 7. So one number in between is 6 plus 2 is 8 upon 7 plus 3, 10. Is the number in between 2 by 3 and 6 by 7. Okay. Then again, in between these two, it is 10 by 13. Here it is 14 by 17. Again, likewise, you can find many numbers. In between these two, 18 by 23. In between these two, it is 22 by 27. So likewise, you can find as many numbers as you want in between any two given rational numbers. Of course, it is in p by q form, right? Okay. So we have seen how to find out rational numbers, or in this case we have seen irrational number also. we can find out. Okay, fine. Now fine, irrational numbers. So we saw how to find out numbers in between two given numbers, rational or irrational also we can find out. Okay, fine. Now I have said that real number line has rational numbers as well as irrational numbers on it, right? Okay. If this is the real number line, it will have real rational numbers, irrational numbers as well. Okay. So rational numbers representing them is not a big deal. Let's say any rational number, 1.1, let's say 1.1. Can I represent this? Yes, this is easy. Let's say this is 0.1 and this is 0.2. Okay, so what you do? So 1, so this is what? 1 and point 1 more than 1. Okay, point 1 is what? 1 by 10. Point 1 is 0.1 is 1 upon 10, so 1 in 10, right? So after 1, just this one, you 1 2 3 4 5 6 7 8 9, just divide in 10 equal parts and just take 1. So I can say that okay, this particular point, this number is what? 1.1. This is 1.1. So any number I can do the same, maybe 1.23. How to represent this? We can represent this, the separation between 1 and 2, you divide in 100 equal parts, okay, and they take 23 out of them, right? This is what? 1 plus 0.23, that is 1 plus 23 upon 100. So the next, the separation between 1 and 2, divide in 100 equal parts, take 23 parts out of that. Okay, so let's say somewhere it will be here 1.23, right? So this is how I can certainly say okay, I can find out any given decimal number, okay, or any rational number. If you want to represent fractions, we can do like where we have done for 23 by 100, any fraction number, of course we can divide the number line in equal parts and then get the desired number I can represent. Okay, so this is easy to understand. But I have said that there are irrational numbers also on the number line. How to find out them? How to, if I say that square root 2 is an irrational number. This is an irrational number. This is certainly on the number line. This is on the number line somewhere. But then how to pinpoint the point? Okay, this is root 2. How to find out that point? Because this cannot be represented in the form of some terminating decimal. Okay, any non, even a rational number, even if it is non-terminating, it is recurring and can be converted to p by q form. Okay, fraction form, so that can be then represented. But irrational numbers, I cannot say that this is equal to 1.414. No, this is just the approximate value. This thing continues. Okay, random numbers will come one after the other. Okay, so then how to exactly represent this? Okay, this is the trouble. Okay, so the method here we'll be using will be taking the help of geometry. Okay, we'll be taking the help of geometry for this. How? We'll be taking, like for example, square root 2. What you can do for representing root 2, what we can do, let's, you know, to represent root 2, take number 1 here. Okay, let's say this is 1, okay, this is 2, this is 3 on the number line, okay, and draw this line and take 1 unit here on the y-axis also. So this is also 1, 2, let's say on the perpendicular to this, okay. So this is 1 and this is also 1. Now if you join this by Pythagoras theorem, we can say that this is equal to what? 1 plus 1 and square root of that, that is square root 2. So that length of the hypotenuse is certainly root 2. Okay, that length, that amount of length is root 2. This much we can very confidently say. So what you do, just take your compass, measure this length like this, and then the same amount, what we can do, put one end here and then put a arc like this. So whatever, wherever it is cutting, that particular point is root 2. Okay, fine. So with the help of geometry like this, we can find out. Okay, but then how to do this for any number? I wish to find, let's say, the square root of 6.5. Then how to find this number on the number line? Okay, for that we'll see how. Okay, let's say I wish to represent root of any number. In fact, let's take root of any number x. Okay, any number x, square root of x. X can be any rational number, of course, square root, because square root of that is going to be irrational most of the times. Okay, it can be a perfect square and become rational also, but square root 3 or square root 6.5, for example, square root of 6.5, this is an irrational number. How to find this number on the number line? Okay, so for that, what you do, so I'll just do this for root of any number, root of x. Okay, so I will just generalize the thing. Okay, so what we do, just take the number, a line segment equal to length x only you take. Okay, the length of, I wish to find out square root x. I have taken a line segment of length x. Okay, so let's say this point is A, this point is B. Okay, extend the point B, the line, extend this line by 1 amount. So this BC is equal to how much? 1. BC is 1, AB is the length x, okay, in magnitude. Now taking AC as the diameter, okay, AC as the diameter, that means the midpoint of AC, you just draw this semicircle. Okay, you draw this circle like this. O is the midpoint of A and C. Okay, AC as the diameter, we draw this circle and then we draw a perpendicular at this point here, perpendicular at this point B. Now let's find out what is the length, this length, let's say name this D. We'll try to find out what is the length of BD, that perpendicular. Okay, AB is x. Okay, so what is the length of OC? OC, the length, the radius of that circle is going to be x plus 1 upon 2. Correct? Fine. Half of the whole AC, that is the radius OC. Correct? Now what is the length of OB? OB is OC minus that 1, that is x plus 1 by 2 minus 1, that is x minus 1 by 2. So OB is x minus 1 upon 2. OD is what? OD is the radius only, right? OD is the radius, x plus 1 by 2, and this thing here is x minus 1 by 2. So can we use the Pythagoras theorem to find out BD from here? Yes. So BD is nothing but, or BD square is what? Hypotenuse square x plus 1 by 2 squared minus x minus 1 by 2 whole squared. simplify this and see what we are going to get. So we can use the identity a square minus b square to solve this. So this is in the denominator, there's going to be 4 and then x plus 1 whole square minus x minus 1 whole square. Okay, so we'll use the identity a plus b and a minus b. Okay, so I'll just write the identity a square minus b square can be written as a plus b times a minus b. This is an algebraic identity. You want to use this, you use this. Otherwise, you can simply simplify this. You'll find this. Okay. So simplify. So that is going to be a plus b. That is going to be 2x, and a minus b is equal to 2. Okay. So this is what 4 gets cancelled. X only. So bd square is x, right? Bd square is x. Bd square is coming to be, this thing is what, x, bd square. So bd is what, root of x, right? Bd is root of x, right? And that is what we wish to find out. So that length, geometrically bd is root x. I cannot exactly, using decimals or fractions find out where exactly a rational number is on the number line, but yes, geometry comes to our help. And certainly this length BD is root x. So you can take a compass, measure that length BD, okay, and then maybe you have the number line here. Maybe this is your number line. This is your 0. Measure this using this compass, a compass BD, and then just draw an arc equal to BD. Arc length equal to BD. So this point here you can say is what? That root of x. Okay, that is the length, same as BD, and this is the particular point. Okay, so this is how we can represent an irrational number on the number line. Okay.